Hey, in this video, I'm going to be sketching a double replacement reaction when we consider limiting reactants. Basically, there's something new that we need to add to it, in addition to what you learned back in Unit 7 with sketching double replacement reactions. So this is a continuation video from the limiting reactants video. So this is the last problem where we have a double replacement, solution of copper 2 sulfate, and a solution of potassium phosphate. So I tell you the mass of both of these. Because you're given both reactants, that's how you know you have to do the limiting reactant check. We already solved for the mass of the precipitate. We already solved for the percent yield. We're just asked for the sketch. Now remember, for sketching double replacements, we do beaker plus beaker. Let's see that. Yields third beaker. And the aqueuses are split up into ions, and the solid is together at the bottom. So in my first beaker, you should sketch this along with me in your notes there. In the first beaker, we have a copper ion with a charge of 2+, and a sulfate ion, SO4, with a charge of 2-, like that. In my second beaker, we have potassium, which is K+, phosphate, which is PO4 3-. Remember, we don't need you to show 3 potassiums and 1 phosphate. We'll violate the conservation of mass for the sake of the sketch for this. All right, in the last beaker, we have Cu3PO4 2 solid. That's a precipitate. It sticks together and it's at the bottom. So you write it as that formula at the bottom of your third beaker. Cu3PO4 2 at the bottom. And I like to draw my little line over it to show that it's like an actual precipitate that settled out. In my other one, I'm covering it here, but K2SO4 aqueous. So I'm going to have K+ and SO4 2-. Okay. Now, before we add the new thing, let's add our waters. Remember, the water is the O with the 2 lines, and the O, the oxygen, is the partially negative side, which points towards the positive ones. So you want to make your oxygens moving towards the positives and away from the negatives. Think of them like little tadpoles or little fish swimming away from the negative things in their life and I did one wrong. And swimming towards the positive things in their life. So you want 2 or 3 waters per molecule, something like that. So take a quick look, make sure your sketch looks like mine, where you have the oxygens facing towards the positives and the negatives, and the 2 hydrogens facing towards the negatives. Now, this is exactly what you would have done back in Unit 7 a couple weeks ago. But because we know that there's an excess reactant, one of these is the excess. Which one? It's the K3PO4. This is my ER. So because this one is my ER, we're going to have a little bit leftover potassium ions and some leftover phosphate ions. So K+ and PO4 3- are left over. So when in our final beaker, now you're always going to have one of them present because it's part of your aqueous product. Notice we had potassium sulfate, so that's why we already have K+ there. You don't need to add more K+, you can if you want, but you do need to add the other aqueous ion, in this case, phosphate. So because potassium phosphate was the excess reactant, we have to make sure we have both potassium and phosphate in our third beaker. So I'm going to add PO4 3-. I'm going to show a couple waters with their with their hydrogens pointing towards it. There's what I added right there is my phosphate. This is now complete. Well, there's one thing I forgot. At the bottom, we should write does not obey LCM. Does not obey LCM, which is of course law of conservation of mass. This basically means we're showing which ions are present, but not the proportions in which they're present. So that's how we sketch double replacements. If you want to sum it up in one sentence, you do what you did before, but you take your excess reactant, you make sure both of those ions are present in the final beaker, meaning you're going to add one ion, the only one that's missing. Okay. Good luck, everyone.